This video is an introduction to Chapter 16. We're going to start off by looking in the table of contents. So we just finished chapters 12, 13, 14, and 15. In Chapter 12, we had kinematics of a particle, so that was position, velocity, and acceleration in time. Then in Chapter 13, we looked at kinetics of a particle, where we used Newton's second law and looked at force and acceleration. In Chapter 14, we did the work energy conservation law, and in Chapter 15, we covered the impulse momentum conservation law. All of this was for a particle. And now, in the next 4 chapters, we're going to look at the same 4 topics, but now for a rigid body. So in Chapter 16, we're looking at kinematics of a rigid body, so that will be angular position, angular velocity, angular acceleration for a rigid body. So how that rigid body moves. And then in Chapter 17, we'll look at kinetics, so force and acceleration for the rigid body. And then in the next 2 chapters, we have our conservation laws, so work and energy for the rigid body and impulse momentum for the rigid body, and that will conclude the course. So now you can turn to Chapter 16 in your textbook. We're going to start off by defining the rigid body. So I didn't see this definition in your textbook, but for a rigid body, if you pick 2 points on the rigid body, so let's say the tip of the pencil here and the end of the pencil here, no matter how the pencil moves, those 2 points are always staying the same distance away. So this is a good example of a rigid body. If you have something squishy, then if you pick 2 points on your object and you squish it, the distance between those 2 points is changing, so that would not be a rigid body. So if you have something squishy, the distance, if you choose any 2 points on the object, the distance between those 2 points is not necessarily staying the same, so that would not be a rigid body. On the next page, which is page 320, they introduced 4 different types of motion, which is in figure 16.1. So we have rectilinear translation here, and you should be reading through this on your own. But for rectilinear translation, as the object moves through space, if you pick 2 points on the object, so let's do the end of the pencil and the tip of the pencil, those points are moving along straight lines. And if you look at curvilinear translation, if you pick 2 points on the object, the motion is along curved lines. So that would be moving like this, as they show you in figure 16.1b. For part C, we have rotation about a fixed axis, so that's what they show you in part C. That would be motion like this. And then in part D, we have general plane motion. For general plane motion, we have a combination of translation and rotation. So here we had rotation, here we had translation. And for general plane motion, it's a combination of translation and rotation, but the rotation has to be on an axis which is perpendicular to the plane that the object is moving in. So that would be something like this, moving in a plane and having your axis perpendicular, so rotating like this as you move in a plane. It would not be something like a football or a screw as you're screwing it into a piece of wood. So if you have your axis of rotation like this and the object's moving in this direction, so moving and traveling in the same direction as the axis of rotation is in, that is not general plane motion. Okay, and then for figure 16.2, they give you examples of these 4 types of motion. So we have rectilinear translation, where the object here is just moving back and forth. Curvilinear translation, so this is moving, this piece is moving like this. That's curvilinear translation. We have general plane motion for this piece here, which is rotating and also translating. And then we have rotation about a fixed axis here and here. Okay, so that's section 16.1. In section 16.2, they look at position, velocity, and acceleration. You can read through that on your own. That brings us to section 16.3. In section 16.3, they talk about angular position, angular displacement, and angular velocity. These equations are on the equation sheet, and you should notice that they're very similar to what we had in chapter 12. So velocity is the derivative of position with respect to time. Angular velocity is the derivative of angular position with respect to time. Acceleration is the derivative of velocity with respect to time, and angular acceleration is the derivative of angular velocity with respect to time. If your acceleration is constant, then you have the same relationships here for constant angular acceleration as we had in chapter 12 for constant acceleration. So the problems can be solved pretty much the same way. You just have angular position, angular velocity, and angular acceleration instead of the position, velocity, and acceleration we had in chapter 12. And remember in chapter 12, if you take this equation and this equation, it implies equation 12.3. So this is not a unique equation. It was derived from equation 12.1 and equation 12.2, so you don't have to use this equation as long as you have 12.1 and 12.2. Similarly, we have equation 16.4, which is like equation 12.3, and that equation can be derived from 16.1 and 16.2, so it is not a unique equation, but it's helpful to use this in circumstances where we don't have information about the time and we're not interested in finding the time. Okay, so that covers page 322 and page 323. On page 624, they're giving you a relationship between the velocity and the angular velocity, both the magnitude, which is equation 16.8, and in equation 16.9, here we have the velocity vector. So this is how you can find the direction of the velocity. You take the cross product of the angular velocity and the vector r, which goes from the origin to the point of interest. And this gives you the direction of the velocity of this point. In order to do this, you have to know what the direction of the angular velocity is. So if your object, let's look at figure 16.4. If your object is rotating like this, you can put your fingers in the direction of the rotation and your thumb points in the direction of the angular velocity vector. So when you curl your fingers in the direction that the object is rotating, your thumb gives you the direction of the angular velocity vector. So if you have something rotating in this plane here, it can either be going clockwise or counterclockwise. If it's going counterclockwise, that vector is pointing up. If it's going counterclockwise, that vector is pointing down. So if we have angular velocity pointing up, so let's say for this picture here, angular velocity is pointing up and r is going this way, so like this, my thumb gives me the direction of the velocity vector. In this situation here, those vectors are perpendicular to each other, so the magnitude is just omega times r. Okay, so that is equation 16.9. And equation 16.10 here is one of the equations on your equation sheet. I did not give you equation 16.8 on your equation sheet, but you can figure that out from equation 16.10. Then we have something similar for acceleration on page 325. We have the tangential component of the acceleration and the normal component of the acceleration. You can read through page 325. And we talked about normal and tangential components of acceleration back in chapter 12, and we had equation 12.18 for that. And we also talked back when we studied chapter 12 about the relationship between this and the angular velocity and the angular acceleration. So let's go back and take a look at that. So this is equation 12.18, which we have here. And for circular motion, the radius of curvature that we have here is equal to the radius. So we have our equation for acceleration here, replacing rho with r, which is the radius. From chapter 16, so that's on page 325, the tangential component of the acceleration is the angular acceleration times the radius, and the normal component is the angular velocity squared times the radius. So now we want to compare that with what we had in chapter 12. So v dot was the tangential component of the acceleration. that tells you how the speed is changing, and that's related to alpha times r. Remember, the angular acceleration tells you how this angular velocity is changing. If you multiply that by r, you get how the speed of the object is changing. The normal component that we have in chapter 16 is omega squared times r, and in chapter 12, the normal component of the acceleration was v squared over r. So those should be equal to each other, which would give us this relationship here. Then if we multiply both sides by r, we get omega squared times r squared is equal to v squared. And if you take the square root, that just gives you equation 16(8). So that equation is true. Okay, so it's similar to equation 12(18), but with the angular variables instead of what we had back in chapter 12. And you can read through the rest of the chapter, paying special attention to what they give you in the green box on page 327. And that concludes our introduction to 16.1, 16.2, and 16.3.